So this is Edexcel June 24 for the Maths Core Pure 1 paper. Question 3. It's a polar coordinates question, and eventually we're going to be finding this area around here, I think, is what they're ending up with. But there's a little part A, and the little part A tells us that the circle, I'm just trying to read this now, has a radius of 6 meters, and that the edge of the circle is 0.5 meters away from the shortest distance. So basically what they're saying is this distance here is 0.5 there. And we know that the circle has a radius of 6. Is that right? I'm just going to quickly check against the question. Yeah, 6 meters. So this distance all the way here is 6 meters, all the way to the edge there, which means that is obviously got to be 5.5 meters. Now, what they're basically then saying is, right, how do we know what A is from that particular perspective? Well, we can see that therefore the furthest distance from the pole's right in the middle, that R is 5.5. So that's going to be our furthest distance. R is going to be worth 5.5. So we've got to kind of look at our equation really and say, right, when am I going to get my most maximum value here? When am I going to get R being worth 5.5? Well, for R to be worth 5.5, I suppose the easiest thing is to realise is this is going to vary depending on our angle theta and give us sine 3 theta. And we know sine goes from 1 to -1. So because we're subtracting this is going to be at its maximum when sine 3 theta is going to equal -1. Because when it's -1, that minus will go with a minus there. We're going to get a plus. We're therefore going to get the biggest value of R. So actually, our biggest value of R is going to be when A is -1. So it's going to be 4 minus A, which gives us 4 plus A. And we know that maximum value is at 5.5. So 5.5 equals 4 plus A, which means A is 1.5. And that's how we work out what that A value must be. And it's all about, usually with these kind of questions, looking at the trig function and just going, right, when's it at its maximum? When can I maximise this? Realising that sine goes between 1 and -1 and thinking how that's going to affect our value of R. So anyway, A being 1.5 is going to be our answer there. Then it says, using algebraic integration, determine according to the model the exact area of T. So we're going to find this shaded area here. Now, the basic idea is, well, if I want to find the shaded area, I find the area of the whole circle and then subtract the area of the shape of the swimming pool, I think this is. Now, we don't have any concerns here at all about negative values of R or anything like that, because you can see that R is perfectly defined for every single value here. There's no place where it comes back into the pole and you're kind of going, there's a value of theta where suddenly we're going to get a negative R, and we might have to think about where we integrate between. Because it seems valid every single point all the way round, we can just integrate between 0 and 2 pi. So that's what we're going to do. So A is 1.5 here. I'll cheat and change that to give us a little bit of a... So we're going to integrate between 2 pi and 0. And like I said, if we were going to have some negatives, you might want to split this up into like 3 segments or something like this, integrate and use the symmetry to just find one segment and times by 3. So you've always got to have it in your mind, is R going negative at any point? Is this going to affect my area? But in this case, no, we don't. R is defined all the way around, so we can just literally do 0 to 2 pi. Half R squared, d theta, is our formula that we can just trot out. So let's put that in there. We're going to get a half integral between 2 pi and 0 of this squared. So that's 4 minus 1.5 sine 3 theta squared. Now, at this stage, we might decide that 1.5 is going to be causing us a little bit of a problem. We could take that 1.5 out certainly write it as 3/2 possibly. So you could play around with that if you want, kind of take that out as a factor so we get a nicer value here. But I don't think we're going to gain too much from this. So I'm going to multiply this out. Let's change that 1.5 to 3/2. Make our life a lot easier. So squared, so it's a double bracket obviously. Ooh, where's the d theta? Let me get a nicer pen as well. See, hopefully this one's nicer. Oh yeah, look at that. Right, so between 2 pi and 0, multiplying that out, what are we going to get? We're going to get 16, then that times that twice, so 4 times 3/2 is going to give us 6 with twice, that's 12 sine 3 thetas. That's right, isn't it? Yep. And then that times itself gives us plus 9/4 sine squared 3 theta. And that is what we are going to have to integrate. Now, quick rundown there. No problem, we can integrate that, we can integrate that. Sine squared. We're going to have to do our conversion for sine squared. Now, sine squared, we usually go to the double angle formula and change it into a cos. I always have to, for some reason, I can never remember the double angle. I have to kind of work it out from first principles, well, not from first principles. I remember the cos squared minus sine squared is cos 2 theta. And then I have to kind of change it around. I have to change that to 1 minus sine squared. So I get 1 minus 2 sine squared theta is cos 2 theta. I don't know why I'm showing you this, my particular lack of memory on this kind of thing. But I can then rearrange that and I get the sine squared theta is 1 minus cos 2 theta halved. This pen's starting to go as well now. So that's why I'm going to change sine squared. Obviously, because I've got 3 theta there, I'm going to change it to 6 theta. So it's now going to become a half integral 2 pi 0 16 minus 12 sine 3 theta, which we'll deal with in a minute, 9/4 times, right, this is going to become 1 minus cos 6 theta over 2. So I'll tell you what, I'll bring the 2 out there to make it that 8 instead of that, and it's just going to be 1 minus cos 6 theta d theta. Let's get rid of all this now. Give ourselves a little bit of space. 6 theta d theta. All of that. Right, okay, now we can integrate. So, half, quickly change pen again. My pen's running out quite quickly. Let's have a look at one here. Right, obviously 16 integrated is 16 theta. 12 sine 3 theta, so that goes to, integrated goes to negative cos. So that's going to become a plus. We're going to have to divide by the 3 there. So that's going to become 4 cos 3 theta. Okay, so sine goes to cos, sine goes to negative cos when you integrate it, and so with minus that becomes plus. Divide by the 3 theta because the differential sign is 3. 3 theta is obviously 3, which we have to divide by, and we get 4 cos 3 theta. Right, let's leave the 9/8 there. Integrate 1 theta. Integrate cos 6 3 theta. Cos goes to positive sine when you integrate it, so it's minus 1/6 sine 6 theta. And that is between 2 pi and 0. So, I think you're going to have to be a little bit careful here about, well, do I tidy this up or not? You could put that 9/8 theta with that 16 theta there. I don't think there's anything massively to gain there, so I'm just going to plug these straight in now. You might tidy it up, like I said, and just find it a little bit easier. Whoops, right, so if we put 6 theta in there, 2 pi in there, sorry. So 2 pi turns out that gives us 32 pi. Right, cos 3 theta, so cos of 3 times 2 pi, so that's going to give us cos of 6 pi, and 6 pi going round is basically the same as 0, because obviously every 2 pi is a revolution. So we're going to go all the way round to cos of 6 pi. Obviously you can put these into your calculator if need. Cos of 0 is 1, so that's just plus 4. Then over here we're going to have 9 over 8 times theta, 2 pi. Sine of 6 theta, well 6 times 2 pi is 12 pi. 12 pi is 6 revolutions, so it's the same as sine of 0, and sine of 0, 0. So, great, we can ignore that. That's the first bit. Subtract a half of, right, putting 0 in there, nothing. Cos of 0 is 1, so times that is 4. 0, and then sine of 0 is nothing, so it's literally just take away that. Right, tidying up time, see if I squeeze it down here. 9 over 8, so that's 9 over 4 pi, on to 32 pi, so let's just quickly sort that out. What did I say? 9 over 4 plus 32, 128 plus 9, is that 137 over 4 pi? My word, I hope that got that right. And then over here we're going to have 4, we got minus 4, oh they're going to cancel. So isn't that just 137 over 8 pi? Let's hope I got that right. Got it wrong, well done me. Oh no, because I haven't actually taken it away from this area of the circle yet. Silly me, that is correct. That's the area of the pool. So now we're just going to do area of the circle, which is just pi r squared, good old pi r squared, so pi times 6 squared. So our final answer is going to be pi times 6 squared, so 36 pi. So this is what they call in this area, T. Area of T is 36 pi minus 137 over 8 pi. Is that right? Yep. And that gives us 151 over 8 pi. I didn't do that very quickly in my head. I just saw the answer. And there we go. All done. So I don't think too bad a polar coordinate one really. We didn't have to do anything like think about negative r's and limit our area that we were going to find between. And the actual integration wasn't too bad. I mean, that's something you might find on single maths, I think, because there's, you know, that's a classic changing the sine squared into double angle with cos. So yeah, that's all right, not too bad.